Alright, we're going to continue graphing our trig functions. We only had the opportunity to look at sine yesterday, so we're just going to keep trucking through. Next one will be cosine and tangent, and we'll take a look at the reciprocals. So on page 413, we're going to check out cosine. And just like we did sine yesterday, we're going to develop a table of values, and then we'll go ahead and plot those points.
There was no asymptotic behavior yesterday, right?
Say it again?
There was no asymptotic behavior
No.
yesterday.
No asymptotes yesterday. We might see them today, though. Okay? All right, so let's think about our unit circle to help us fill out this table. If we are at the 0 angle mark, that's our very first point on the right-hand side. The ordered pair is 1, 0. So we need the cosine value from that point, which would be an x value, so that would be 1. All right, pi over 4 is in the very middle of the first quadrant. The ordered pair is the square root of 2 over 2 for both of them. So the x value, square root of 2 over 2. As a decimal, that would be 0.707, yada, 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 if you were to use your calculator. All right, pi over 2, it's at the very top. Ordered pair is 0, 1. So x value is 0. 3 pi over 4 is in the middle of the second quadrant. So what would our x value be there? Yeah? All right, and since we're in the second quadrant, positive or negative? It'd be negative. Good. All right, pi is the very left point. Ordered pair, negative 1, 0. So x is negative 1. 5 pi over 4, middle of the third quadrant. Yeah? Perfect. All right, 3 pi over 2 is at the very bottom. Ordered pair 0, 1, so x would be 0. 7 pi over 4, middle of the fourth quadrant. Go ahead. Uh-huh. And then 2 pi, back to where we started, value of 1. All right, so now that we have the table, we'll go ahead and plot some points and see what this cosine graph looks like. All right, so there's one cycle of our cosine graph. Notice how if you were to continue the same pattern, it would probably be a wave, okay, just like sine was. But it's not the same exact wave because we're starting in a different spot. Notice how the cycle or the chunk of graph that repeats itself was different than the one we saw for sine yesterday. So maybe we can make note that the cosine graph starts at 1, okay, the y value of 1, whereas sine yesterday started at the origin. So they can be kind of confusing, okay, they're both waves, but it just depends on where you're starting. That determines whether if it's sine or cosine. All right. Let's see if we can talk about some transformations. If we wanted to stretch this graph at all, how those might affect the shape. Take a look at the bottom. We have 3 times cosine. Can you describe what type of transformation multiplying on the outside would do? You can look back from yesterday if you need help. Yeah. The amplitude, okay, the height of your graph. So this, in terms of transformations, this is a vertical stretch. Maybe I'll do VS for short. Specifically by 3. So what we're going to do is we're going to change the amplitude. How about we go ahead and list the original period and amplitude for cosine, and then we'll see how those change. So based off this original black parent function we have, what's the period? How wide is that cycle? Yeah? 2 pi, good. And then the amplitude, you first got to find the baseline or the middle of the graph. What's the amplitude of that cosine wave? How far up or down do you have to go? Yeah? Say it again?
2.
Oh, it's 2 tick marks, okay, but that just represents a distance of 1, okay? All right, so our amplitude is 1. So if we're vertically stretching this graph, we're only really changing the height of the graph. We're not changing the width. So the new amplitude should be 3, and we're not changing the period, so it's going to remain a 2 pi. So what this might look like is it's still going to go from 0 to 2 pi. It's still going to be in that little section, but instead of going up 1 or down 1, you now have to go up 3 or down 3. So these high points and low points, we'll go ahead and stretch those. But the x-intercepts are going to stay exactly the same, because though those y values are 0, and if you multiply those by 3, they're not really going to change. So we're going to keep the same basic shape, but notice how we vertically stretched it. We made it a very tall wave. All right, maybe we want to label that one as 3 cosine theta. Obviously, if we wanted to, we could continue the pattern, okay, because this would be a periodic function. But so our paper doesn't get too busy, I think we'll just go ahead and keep it to 1 cycle. Okay, but realize you could continue the pattern. What about the next one? Cosine of 1/2 theta. How does that change our graph? What do you think, Marie? There we go, horizontal stretch by 2. It's kind of the opposite of what you would think. Even though it's a 1/2 in there, we're actually multiplying by 2. So horizontally, meaning left or right, that means we're affecting the amplitude, or the period rather. Okay, how wide the cycle is. We are not changing the height. Yeah?
It was cosine of 2 theta when you multiply by 1/2.
Yes. Good. All right. Can we think about what the period and amplitude would be of this function before we graph it? If we're horizontally changing it, what do you think, Marie?
We have an amplitude of 1 and a period of 4 pi.
And a period of 4 pi. All right, so we're not changing the amplitude. That means the original amplitude of 1 is going to stay the same. But we are horizontally stretching by a factor of 2. So if the original period is 2 pi, we have to double it, and that would make it 4 pi. So let's see what this graph might look like. So we're going to take the points on the black graph and double all of their distances. So let's pick some points. This first starting point has an x value of 0. So if we multiply that by 2, that's really not going to change. The next easy point is probably the x-intercept at pi over 2. Notice how that's 2 units away from the y-axis. So if we double it, it should be 4 units away. All right, so it's going to move 2 units to the right. The bottom point is 4 units away from the y-axis. So if we double that, it should now be 8. The next x-intercept is 6 units away, so now it should be 12. And the ending point on our cycle is 8 units away, so now it should be 16. So if we connect all of those red dots, there's our 1 cycle just stretched out. And notice how it ends at 2 pi. Or sorry, 4 pi. Like we said the period should be. We doing okay from yesterday? Coming back a little bit. All right, let's try this one as an example. What if we had, let's say, 4 cosine of 4 theta minus 3? Can you list, okay, we're not necessarily going to graph this one, but can you list some of the transformations and perhaps how those affect the period and amplitude? What do you think?
The minus 3 would be the baseline.
Baseline. All right, so that's the middle of your wave or the middle of your graph. Because everything's shifting down 3. That affects the middle, yeah.
Would the period be 1/4?
Close. Okay, so we would have to multiply the period by 1/4. Okay, so if you were to take 2 pi times, bless you, times 1/4, what would our new period be? Bless you. 2 divided by 4 would change to 1/2, yeah? Pi over 2. Okay, there's your new period. All right, so it's not necessarily the number itself. We have to multiply by that number. So far, so good. What about the 4 out front? Yeah?
The 4 affects the vertical stretch.
That's your vertical stretch, so that's representing your amplitude. Okay, so the middle of your graph is at -3, and from that middle, you are stretching up 4 and down 4 to get to the high and lowest points on your wave. Good job, guys. Okay, we're going to keep practicing that for all these other examples. So let's go ahead and take this cosine information that we just discussed, and on page 411, we'll fill in the table for cosine. So we said that cosine starts at the y value of 1. Cosine is a wave, so if you continue it forever to the left and forever to the right, it would have a domain of all real numbers. Let's see, cosine also had a period of 2 pi. There were no vertical asymptotes. What about the range of cosine? If you take a look at our original black graph, before we transformed any of it, how low or high did it go? Yeah? There you go. So if you take a look at these characteristics, notice how sine and cosine are basically the same. It just depends on where they start. That's the major difference between the two. Sine starts at the origin, cosine starts at 1. All right, let's go ahead and check out tangent. How is tangent related to the x-coordinate and the y-coordinate on our unit circle? Yeah? Y over x. All right, so if sine was related to y and cosine was related to x, tangent we could also think of as sine over cosine, okay, in terms of those trig functions. So let's check out our table here. Our first ordered pair at the beginning mark is 1, 0. So for tangent, we need to take the y-coordinate divided by the x. So that would be 0 divided by 1, which is 0. Pi over 4 in the exact middle. Square root of 2 over 2 for both of them. We need the y-coordinate divided by the x-coordinate. Yeah, 1. Good, they're exactly the same. Pi over 2, very top. 0, 1. What would our tangent value be? Yeah. Asymptote, right, undefined. All right, 3 pi over 4, middle of the second quadrant. Can we think about what the y value divided by the x value would give us? Yeah? -1, good. It's the exact same as the middle of the first quadrant, just the x value is negative because we're in the second. Pi, we have negative 1 comma 0. So y divided by x would be 0. 5 pi over 4, middle of the third quadrant. What would the y divided by x give us? Yeah? Positive 1, good. They're exactly the same and they're both negative. 3 pi over 2, very bottom. 0, negative 1. Y divided by x. Yeah? Undefined, yep, another vertical asymptote. All right, 7 pi over 4, middle of the fourth quadrant. Yep. Negative 1, good. And then 2 pi back to where we started. We got 0. All right, let's plot some of these points. 0, 0, pi over 4 and 1. Vertical asymptote. Negative 1, 0, 1. Vertical asymptote. Negative 1, 0. All right, so it might look a little weird just by plotting the points in the asymptotes. We're going to talk about what these points on the end are kind of doing because they're just kind of floating out there right now. But let's go ahead and focus on the portion in between the asymptotes. We know that a graph never ever touches a vertical asymptote. It gets really close, it just never touches it. So if we're trapped in between those asymptotes, we'll start really close on the left-hand side. We go through the points that we plotted kind of in the middle, and then we get really close on the right-hand side. What do you think these dots on the end are representing? I know we got to connect the dots. The question is, where do we go after we connect them? Do we go like that? What do you think? Yeah. There you go. All right, so these 2 points here are the repetition of these 2 points in the middle graph that we plotted. So what we're doing is we're taking this kind of asymptote section of a graph and we're repeating it over and over and over again. So if we were to continue, this dot would come next, and then after that one we would need a vertical asymptote. Okay. Very similarly on the left-hand side, we would need our third dot at negative 1, and then an asymptote after that. All right, so we could keep repeating the pattern if you wanted to, but maybe we'll just keep it to those 3 right now so we don't get too cluttered on our graph. Can we identify the period and the amplitude of our tangent graph? In order to identify the period, you have to first identify the cycle or the chunk of graph that's repeating itself. How wide is the cycle? What do you think, Marie? What do you mean it's only half? You have the right idea of it being half.
It's like a fourth of pi 2.
Okay, so if you take a look at the one chunk that we definitely had in the middle, how wide is that one chunk? How many units? Just count tick marks. You see how it's 4? Okay, so if you were to start at 0 and count 4 units, 1, 2, 3, 4, notice how you'd land at pi. Okay, so our period is pi units. For the other ones we did, like sine and cosine, the period was 2 pi. So Marie was kind of on the right track when she said an idea of a half. Okay, notice how instead of being 2 pi, it's now 1 pi. It has that half relationship. So tangent's a little bit different. Its period is pi and not 2 pi like the other ones. What about the amplitude? Middle of the graph at 0. How high or low does this graph go from the middle? Yeah? None or infinity. Yep, because we have those arrows on the end. So it's going to go forever up or forever down. All right, let's see how some of these transformations would change our graph. All right, multiplying by 3 on the outside. That's going to be our, not vertical asymptote, we have a vertical stretch by 3. Now, we don't really have high points and low points like we did on a wave to stretch, but we do have some points that we would be able to stretch. So maybe we'll use, let's do this middle one that we initially did. These 3 points that we plotted, we're going to multiply their y values by 3. If this y value is -1, it's going to be stretched down to -3. Morning. Who are we looking for? Thank you. All right, so this point on the original tangent graph, we multiplied its y value by 3, so we're down here. The next point is on the x-axis, which is a y value of 0. So if we multiply that by 3, it's not going to change. And the next point we have has a y value of 1. So if we multiply that by 3, we're somewhere right there. So we still are keeping the same shape. Notice how in order for you to connect the dots, though, it's more of a vertical line than the wavy one that it was previously. So we're taking that kind of S curly shape and we're stretching it out, which basically is turning that curve into a straight line. Almost like if you had a wavy string and you pulled it, it would stretch it out. Okay, so we're vertically stretching it, we're making it kind of straighter. So let's see how that affected any of our characteristics. Period or amplitude. Did we change the width of that first, or of that section of that cycle? Is it still 4 units wide? We still have our asymptotes here. All right, so our period is still pi. What about our amplitude? Yeah? It's still infinity, okay? Just like the other ones, and this is where it kind of can be a little thought-provoking, I'd say. For sine and cosine, the amplitude was 1, and we noticed how if we're vertically stretching it, the new amplitude would be that number that we stretched it by. The same thing's happening here. If you were to take infinity, though, times 3, notice how that's still infinity. Okay, so it's still, the amplitude is still affected, we just can't see it because it's still some infinity value. That's what's a little bit different. All right, let's go ahead and try the 1/2 pi. So this would be our horizontal stretch by 2. All right. Let's go ahead and we'll use the same section, okay? Maybe if you want to, just so we're less cluttered, we'll erase the other ones on the end. Okay, we'll just deal with one section of tangent. What we're going to do is we're going to take this section and we're going to multiply it or horizontally by 2. So this asymptote, if it's at pi over 2, which is 2 units away from the y-axis, that asymptote should now be 4 units away if we're doubling its location. So this asymptote is moving here. Let's see, the first dot on our original graph was 3 units away from the y-axis. So if we double it, it should now be 6. So somewhere right there. The middle point on our black graph was 4 units away. So now it should be 8. The next dot on the black graph was 6 units away, so now it should be 12 units away. And our last asymptote was 1, 2, 3, 4, 5. Oh wait, that was 6 units away. 1, 2, 3. This dot was 5 units away, so now it should be 10 units away. And the asymptote was 6 units away, so now it should be 12. Somewhere right there. All right, so if we connect the red dots, keeping inside those asymptotes, there's our horizontally stretched graph. So now notice how it's even curvier, okay, because we're stretching that curve horizontally. We're making it kind of more wavy. Let's see, our amplitude is still infinity because we're not changing that. We're just changing the width. And if we're stretching the width by 2, we need to take the original period and double it. So that would be 2 pi. Now we can check our work. If you were to count from asymptote to asymptote, that would be 1, 2, 3, 4, 5, 6, 7, 8 units. So if you go back to 0 and count 1, 2, 3, 4, 5, 6, 7, 8 units, notice how you land at 2 pi. Okay, that's how wide your chunk is. Let's practice this one. Let's say we had 2 tangent of 1/3 theta plus 3. Can we identify any transformations? We're not necessarily going to graph it. Can we think about what the graph might look like, though? What do you think, Marie? Yeah. The baseline is at 3. So that's the middle of your graph. Okay. Basically, instead of this middle point on your curve being on the x-axis, this middle point would now be at 3. Okay, so everything's moved up 3 units. What else can we identify? What's the 2 doing and what's the 1/3 doing? What do you think, Tori? Go ahead.
The 1/3.
Uh-huh.
That changes to 2 pi.
Close. Okay, so if this is 1/3, we gotta take the original period times the reciprocal of that. Is the opposite of what you would think. All right, so our period would be 3 pi. All right, it's originally pi, but we're tripling it, so that turns into 3 pi. What about the 2 out front? Yeah? All right, so this would affect our amplitude. Now, we would have to take infinity times 2, but notice how that would still be infinity. Okay, so you're not really changing the amplitude per se, but you are definitely affecting the shape of the graph, okay, because instead of being curvy, if you stretch a curve, it's going to turn more into a line. It's going to be a little bit more straight. You doing okay so far? All right. Let's go ahead and see how far we can get on the next one. We're definitely not going to finish it, but maybe we can at least fill out the table. All right, cosecant. Now we're going to start to get into the reciprocals. What's cosecant the reciprocal of? 1 over, yeah? 1 over y. All right, so that would be 1 over sine of theta, if y is sine, yeah?
Did you want to do the chart for tangent before
Oh, thanks, yeah. I'm getting a little ahead of myself. Okay, tangent. This one we can say it starts at the origin. Okay, that middle point that you could plot is right at the origin. All right, domain. Might be a little tricky. We'll come back to that one. Range, negative infinity to positive infinity, because we go forever up and forever down. We have those arrows. Our period was pi. All right, and we did have some vertical asymptotes. Where were they located? Vertical asymptotes at x equals... Can we find those numbers or those values? At least on my paper, we got to look at the black graph. So it looks at pi over 2 and 3 pi over 2. Bless you. All right, and we know we would have more, okay, if we did more cycles. All right, let's go ahead and talk about the domain. We could have all real numbers, but if we have some vertical asymptotes going on, we know there are some x values that we have to skip over. So this is when we're going to try to write that rule. Take a look at where we said the vertical asymptotes are located. Can we figure out a rule that we would be able to use to determine where any asymptote is located? We did this the other day when we were doing the periodic graphs. Let's see. I want you to pick any of these that you want. It doesn't matter which one. You can do pi over 2 or 3 pi over 2. Maybe we'll do pi over 2. And the question is, what's the difference between pi over 2 and 3 pi over 2? What do we have to add to get from the first one to the second one? Yeah? You have to add 1 pi. Right. You can think about this as a half, and this is 1 1/2. So to get from a half to 1 1/2, you have to add 1. So we're going to add 1 pi, and we need some type of n in there to help us determine the number of times you want to go around that unit circle, depending on if you want to find other values to the right or to the left. So we'll go ahead and use that as our rule for the domain. So if you want to list the asymptotes to help you, that might not be a bad idea to help you write that rule. Okay, we're going to have more practice of that when we come through the other ones as well. All right, I think we might have to stop there then, because the bell's going to ring in a little bit. We'll go ahead and come back to this one tomorrow.